Hi, my name is Michael Ross. I will be talking in this presentation about data mining and machine learning, or multivariate analysis, using Natural Resources Canada's Xplore software. So what I will be talking about in this presentation is specifically starting out with some objectives for this webinar, and then introducing the software, the Xplore software. In particular, I'm going to talk there about multivariate data. This is the type of data that Xplore is especially suited for, and I'll talk a bit about what makes it different from data that you're perhaps dealing with on a regular basis. I'll talk about target users for the software, so you can determine whether you fall within that group. And then I'll talk about the techniques or the capabilities of the software in terms of data mining and machine learning. So there we'll look at pre-processing of data, that is cleaning up the data in anticipation of an analysis, transforming variables, getting rid of noise, filtering out data that seem to be outliers. Then I'll talk about principal component analysis, or PCA. This is a technique for getting a global understanding of what the entire set of data is telling you. It does this by reducing a large set of data, that is a data set with many variables, down to a data set having fewer new variables, so it's a new set of variables, but this new set of variables contains a large amount of the information contained in the original set of variables. So principal component analysis allows us to condense the problem or condense the message of the data down to a much smaller set of variables. Then I'll talk about predictive modeling, which is predicting a value of something like a key performance indicator based on data that you're measuring on an ongoing basis. And finally, I'll look at how that, as well as principal component analysis, can be applied to process monitoring and fault detection. Finally, at the end, I'll have a slide about next steps if this is appealing to you. The objectives of this webinar are to introduce the Xplore software and the training that goes with it so you can decide whether it is of interest to you. I'll describe the target user for this Xplore software so you can figure out if you fall within that group. I'll give a sense of what is provided in the Xplore training, and mainly I'll introduce some of the techniques used in Xplore. So what is this Xplore software? It's Windows software developed by Natural Resources Canada. It's a tool for analyzing large sets of multivariate data. So what do I mean by multivariate? Well, firstly, you have many variables. So it's not just a large number of measurements of a small set of variables. It's a large set of different variables. Moreover, some of the variables are correlated. In fact, we would expect many of the variables to be correlated. That is, they are not independent. By correlation, I mean that there is a factor that affects the two different variables such that a change in one of the variables leads to more or less predictable change in another variable. In contrast to that, independent variables change completely independently. A change in one does not allow us to say anything about the probable change in the other variable. So if you have all independent variables, then multivariate data analysis isn't really any different than typical techniques which involve just looking at each variable independently. But often in industrial applications, you do have these multivariate data sets. So some examples of these, which we'll talk about the correlations in them, are measurements of temperatures at different locations within an oven. So looking at the top right here, we see that we have an oven as represented by this rectangle, and we have measurements of the temperature here at T1, at T2, and T3. Because these are all within the same oven, we would expect if we see a very high value for T1 that T2 and T3 will also be high, but they won't be identical, so it's not exactly the same reading, but changes in T1 will tend to be reflected in changes in T2 and T3. Here's another example. Within some sort of vessel, we're measuring temperature and pressure. Since we know that temperature and pressure are physically related, we'd expect to see correlations in these two measurements. And finally, down here we see another way that correlations can arise. Imagine you have product running through some sort of process here, and we take measurements at 3 points in time in the process, or 3 locations in the process. So evidently, if some product is coming in at a very high temperature, you would measure high temperature at T1, but at some later point you would measure also a high temperature at T2, and further along a high temperature at T3. So there's a correlation between T1, T2, and T3 here. It's a correlation with a lag in time, however. These types of data sets where you have these correlations are the types of data sets that require some special techniques to deal with those correlations, and Explore software does that for us. Let me expand on that last point. What is special about these multivariate data sets that we need a tool like Explore? Well, first, there's going to be tens or hundreds or thousands of different variables. Furthermore, the correlations between the variables may not be obvious. When you're first looking at the data set, you may not know which variables you can expect to be correlated. Because there are correlations between the variables, and the variables are not independent, they contain redundant information. So we don't need that redundant information, and it allows us to simplify the data set. One technique we often use for analyzing data sets is regression. For instance, multiple linear regression. When you have correlated variables, it can be hard to apply that standard technique because the regression coefficients can be hard to determine. First, because you have so many variables to deal with, therefore making it a very big problem. But second, because the correlations between the variables lead to unstable solutions for the coefficients on the regression equation. Finally, you may want to predict values for multiple correlated variables. Typically in multiple regression, we'll be using many input variables to predict the value of a single output variable. But you may in fact want to predict a suite of output variables, and in fact we may want the correlations between those output variables, between themselves and with the input data, to be reflected in our predictions. In practice, these types of multivariate data sets arise in measurements from industrial processes, and that's what we're focusing on here, but also in measurements of building environmental variables and mechanical system control variables, and in completely different situations as well. Just one example, satellite measurements of reflectance at different wavelengths. What did I mean by analyzing data exactly? Well, the first step is going to be ingesting and cleaning the data, so getting it into your software tool and cleaning it up so that you don't have a problem where outlier values sway unduly your analysis. Then you're going to do some data mining. You're going to investigate the relationships between the different variables. And one technique that's very useful for this is to reduce the number of variables you have to look at down to a smaller set of new variables that we'll call the principal components. The principal components allow us to look at a small set of variables, say 3 to 5 variables, instead of a large set of variables, say 10 or 100 or 1,000 variables. And obviously it's a lot easier to understand and get a handle on what's going on in a small set of variables than a very big set of variables. Then we want to build models that generate predictions of the values of key variables. We can use linear models based on the principal components. So there's techniques for deriving those models. And then there's also machine learning techniques where we use an artificial neural network to predict the values of key variables based on tendencies inferred automatically from the training data. Finally, you've got these models either from data mining or from predictive modeling. You may want to apply it on an ongoing basis to your measurements. So this can allow you to track or control ongoing process operation using these relationships uncovered in data mining and making comparisons with predictions of key variables. The target audience for the Explore software, particularly from the point of view of Natural Resources Canada, is organizations that have multivariate data from industrial processes. So let's say you're seeking to reduce energy consumption by 5 to 15% and thereby reduce your GHG emissions, or you're attempting to improve product quality by reducing variability in your industrial process, or you're aiming to improve productivity, perhaps by reducing downtime. This Explore software is meant for you, and it aims to or intends to help you satisfy these goals by identifying low-cost or no-cost measures that reduce variability in your industrial processes, contribute to troubleshooting and the reduction of downtime, and aid in process monitoring and control. However, the tool is not limited to industrial processes. For instance, you can apply it to the satellite data sets that I was mentioning just earlier. So it can be used with non-industrial data. It can be used with building data. The other key aspect of the target audience is you are in Canada and your organization is a Canadian organization. This was developed by Natural Resources Canada for the benefit of Canadian industry. You might ask yourself, do I have to write code to make use of this Explore software? The answer is no. Explore implements a subset of useful techniques from data mining and from machine learning. It's not as flexible as writing code. If you write code in Python or R or whatever the other language you want to use, you can implement whatever you want in terms of algorithms for machine learning and data mining. However, that requires a much more profound knowledge of the field. So Explore implements a subset of those techniques, and it makes those accessible to people without forcing them to have that profound knowledge of the field. So it's easier to use. Now, if you're in the position of already having a team of statisticians at your company writing Python or MATLAB or R code to do the data mining tasks that your organization needs or apply machine learning to various problems, this Explore software may not be the tool for them. They already have very powerful tools. Explore is meant to help people apply their expertise, for example, their process knowledge, to their data, not to turn people into data mining and machine learning gurus. So it's to leverage your process knowledge, your understanding of the process you're dealing with by giving you a more powerful way to understand the data that process generates. How do you get the Explore software? Well, good news, it's free, but of course it's free to Canadian industry. However, NRCan wants to make sure that you know how to use it correctly. They don't want people to be taking this Explore software, attempting to use it incorrectly, and then finding that it didn't work for them and attributing that failure to the software itself. To make sure that you know how to use it correctly, you can either demonstrate that you have a profound knowledge of these techniques, maybe you've been doing this type of stuff for a long time, or you can attend a multi-day training course, and that's the more typical way of getting this Explore software. The advantage of the multi-day training course is that not only do you then learn about the techniques, but you learn about the application of the techniques using this particular software. Explore has a number of capabilities. First, it helps in data import and pre-processing. Second, it does a descriptive or global analysis using principal components, as I mentioned earlier. These are a reduced set of components or a reduced set of variables that describe as much information as possible from the bigger data set. This is useful, this descriptive or global analysis using principal components is useful for recognizing patterns, correlations between data, outliers, trends, and groups. Also, you can look at predictive modeling. So predictive modeling is making predictions based on measurements you have. Two techniques are implemented in Explore: projection to latent structures, or PLS, This is based on the principal components. It's a linear technique. A nonlinear technique that's implemented in the software is artificial neural networks. When you've developed these predictive models and you've developed descriptive or global analysis models, you can apply these to the task of online monitoring and fault detection using Xplore software. I'll look at each of these capabilities in a little bit more detail now. In terms of data import and pre-processing, Xplore does a number of things for us. First, you can get your data into the software from Excel worksheets, from plant historians such as OCSoft Pi, and from SQL databases. Once the data is in the software, you can use it to identify outliers, to clean those outliers and filter data, to figure out problems in your data, to investigate rapidly correlations between your different variables, to transform your variables so that they make more sense for the type of analysis you're doing, and to adjust for time lags. When you look at the percentage of time or effort that is spent in a typical data mining machine learning study on this step of pre-processing data, it actually can account for the majority of time. So that's shown in this graph here, where it can account for 20 to 80% of the time and effort in a typical study. Looking at the Xplore software, you'll see it's got a nice graphical user interface that allows you to see the values of the variables, identify different ranges of variables, either using limits or using a lasso selection tool, so graphically identifying points, to include and exclude different points. It generates automatically statistics like the average, the minimum, the maximum, the standard deviation, both for your original data set and your data set once you've removed outliers. And it provides you with histograms, once again, from before and after data removal. At this pre-processing stage, Xplore helps us quickly identify variables that are correlated. This is a matrix showing the correlations between 29 different variables. So the variables are indicated by numbers along the horizontal axis and along the vertical axis. The strength of the correlation is indicated by the number between 0 and 1 in magnitude at the intersection of the two. So for instance here I have a correlation of 0.88 between variable 4 and variable 14, just by reading that number off the intersection of the two. And that's a positive number, indicating it's a positive correlation. An increase in variable 4 tends to lead to an increase in variable 14 and vice versa. The blue negative values indicate negative correlations, which correspond to an increase in one variable leading to, in general, a decrease in the other variable. So this helps us very quickly identify strongly correlated variables, weakly correlated variables, both positive and negative. Along the bottom, you'll also see miniature versions of scatter plots between each of the two different variables. And this can be helpful when you identify something interesting or surprising in this matrix of correlations, what the actual, what's leading to that correlation coefficient in terms of how the scatter plot looks. You can click on one of these scatter plots very quickly, open it up into a maximized version, and get a sense for how the two variables relate to each other. For descriptive or global analysis, this is the generation and use of principal components, as I mentioned earlier. So to frame this, let's say you have data from a refinery and you're measuring more than 500 variables. This is too many variables to really understand the global situation of the process. Humans aren't meant to understand 500 variables simultaneously varying. In all likelihood, many of the variables are going to be correlated. They're going to contain redundant information. And the principal component analysis condenses these measured variables down to, for example, 3 to 6 principal components or new derived variables. And then the problem of understanding what's going on in this process is reduced to the problem of understanding what's going on in these 3 to 6 principal components rather than looking at more than 500 variables. The nice thing, the two nice properties of the principal components is they capture as much variability in the data as is possible using such a small set of derived variables, and those derived variables are uncorrelated or independent by construction. So we don't have to worry about the correlations between the variables in the principal component space. There are no correlations between the principal components. They are independent of each other. So we can look at each of them in isolation. This is a form of dimensionality reduction, meaning we're reducing the dimension of the problem down from more than 500 variables to, say, 3 to 6 principal components. And here's an illustrative example of what this can do for us. It's from the field of image processing. In the real world, image processing does not make use of principal components. There are more effective ways to process images, but it does work. So we see on the right an image constructed using 120 principal components, which is not the same as saying just 120 points of data. It's 120 principal components with multiple observations along those principal components. In the center image, those are reduced to just 50 principal components, and in the left-hand image, those are reduced to 12 principal components. So a reduction of an order of magnitude from the rightmost image to the leftmost image in the terms of the amount of data. However, we can still understand and see that in this leftmost image that this is a picture of a gentleman wearing glasses, smiling, wearing a button-down shirt. So even though it's a blurrier image, the main major features of the image are still understandable, are still comprehensible from this reduced representation. And that demonstrates that there's redundant information in the original problem, and we can get rid of some of that and still understand what we're looking at without having to look at so many different variables. These principal components are used in a global analysis in two ways. So let's take the example of a system where we have 11 measured variables being condensed down to 2 principal components. So we'll call those principal component 1 and principal component 2. The 11 measured variables are things like oxygen analysis, the efficiency of the process, steam flow rates, airflow rates, pressures, and those are all shown on this graph, which shows PC1 and PC2. This graph over here showing PC1 and PC2 also along these horizontal and vertical axes show the measurements of the process at different points in time. Let's say that we've got a bunch of observations from this process and we look at the efficiency and we see that while much of the time the efficiency is good, it's high, there are 2 different times when the efficiency is low. So the question we might have is, are the 2 periods of low efficiency operation caused by the same thing, or are they 2 different distinct regimes of low efficiency operation? By looking at the principal components, we can get an answer to that question. We can cluster the data into high efficiency points, shown in red, and then low efficiency points at time 1, or during the first period, shown in black, and low efficiency operation points at the second period, shown in gray. And because these form distinct clusters in this PC1 versus PC2 graph, we can conclude that there are distinct causes for the 2 different periods of low efficiency operation. Interestingly, and not at all obvious, but it's something we talk about in the course, we can get some sort of sense of which variables may be driving the process to different quadrants in this graph by looking at where the variables lie in this right-hand graph. So for instance, this low black cluster here would probably have fairly large values of the air, the tertiary air flow for this particular process, because we see that that variable appears with a strong negative value of PC2. So variable observations that have a strong negative value of PC2 are likely going to be strong in this variable 7. That's not obvious, but it's useful once you understand how that comes about to get a clue for what might be causing the clustering of data on this left-hand graph by looking at where the variables are clustered in this right-hand graph. Moving from descriptive modeling to predictive modeling, what is the difference? Well, in predictive modeling, we're trying to predict an important process variable's value. So this might be a key performance indicator, a production rate, the efficiency of the process. In contrast with the descriptive modeling, we were merely trying to say, in what regime am I operating? That is, what is the global message of all the data I'm collecting boiled down to a smaller set of principal components? Now we're actually picking a variable and saying, give me a prediction of this variable. And there's a lot of things we can do with these predictions. We can use it to optimize or improve the process performance. So we can say, if I want to minimize my fuel consumption or maximize my quality or reduce my variability, which measured variables do I need to control to do that? You can also use these predictions to estimate a difficult to measure parameter. In industrial processes, there may be a number of variables that can only be measured in laboratory analysis. Or there may be something like the state of the process that no single instrument can measure. And there may be instruments with large uncertainty margins, so just looking at one or two measurements from those instruments, you're not too sure of what it's telling you. But if you have correlated variables, you can use this predictive modeling to generate a soft sensor that gives you an estimate of the value that you're going to find in the laboratory measurement, or the state of the process, or the correct value for the measurement of the instrument. And having this soft sensor value either to replace or in combination with the laboratory analysis or the instrument measurement can be a really useful thing. Finally, you can use these predictions for control. You can build these models that allow you to better control your process. The principle of predictive modeling is to take a large set of process variables, we'll call those X, that you're measuring on an ongoing basis. So you might have n measurements in time of those variables, to predict some y variables at those same times, but the number of y variables will typically be much smaller than the number of x variables. So the x variables will be things like your process measurements, experimental measurements, chemical compositions, external conditions, and your y variables might be things like energy consumption or production, the quality of your process, some measure of performance like a key performance indicator or cost, the quantity of production or the production rate. So you want to predict those things using your process measurements. And predictive modeling is coming up with an equation that links y to x, using methods that rely on data rather than models derived from physical principles. So one approach, obviously, is to try and understand the physics of what's going on, or the chemistry, chemical engineering of what's going on, and to use those principles to model y based on x. Here with the Explorer software, we're simply using the data itself to help us estimate y. There are a number of different options for doing this predictive modeling. We'll break those down into linear regression models and machine learning using artificial neural networks, which is a nonlinear model. In terms of the linear regression models, traditionally people have tried to use multiple linear regression. However, as mentioned earlier, this has a lot of problems when you're dealing with correlated data sets. particularly very large numbers of variables with correlations. We can get by a lot of those problems by using principal component analysis, either in terms of generating a regression equation using the principal components. For example, instead of using 500 measured variables to predict, say, the energy consumption of your process, you condense those 500 correlated variables down to 3 to 5 variables and then use those in a regression equation. Remember, those principal components are independent as well, so it's going to be much easier to generate a regression equation for the small set of independent variables. So that's principal component regression. There's also an extension of that called projection to latent structures, or partial least squares. Both terms are used. This allows us to generate multiple y variables and to respect the correlations between those y variables when we make predictions. Sometimes our process is not linear, in which case a nonlinear relationship needs to be found between the two, and that's when we can make use of machine learning using artificial neural networks. So how is that implemented in Explore? It's a pretty simple model for a neural network. You'll have an input layer where you have your input variables being fed in. So for instance, x1 would be the value of a particular input. Might be position or time, pressure, something like that. And for each of these input layer variables, we'll multiply the value by a weighting and then feed that into a hidden layer node or neuron. Each of these arrows is therefore associated with a weighting that is applied before the variable is fed into the hidden layer. Within the hidden layer, there is some sort of nonlinear activation function. Here we look at a tangent sigmoid function, so an S-curve that maps input values to output values. So we'll take the weighted inputs, sum them together, feed that into this tangent sigmoid activation function, and come up with an output variable, an output value that then gets multiplied by another weighting and fed into the output layer. The output layer, in Explore at least, has a linear mapping function. So all these 4 outputs of the hidden layer are summed together and pass through a linear function that maps the sum of the inputs to an output value. So this is an artificial neural network. It's based on one conceptualization of biological neural networks. The advantage or the interesting aspect of this is you'll see there's a large number of weightings that need to be determined. We don't have to determine those weightings. Those are determined automatically by a training algorithm that will change the weightings, will adjust the weightings to, as best as possible, map measured values for the inputs to measured values for the outputs. Thus, we'll start with a training data set, which we will use to extract the information necessary to determine the values, the best values for the weights associated with each of these arrows. And then once those values have been determined, we can feed in new data in the input layer and come up with predictions at the output layer. And once again, because there's these nonlinear functions here, it's not just a linear sum of the input variables, it has a nonlinear response to the input variables. Principal component regression and projection to latent structures are very useful techniques as well. So all of these are suitable for high dimensionality problems. So you can have a lot of variables, which is obviously really key for us. Principal component regression and projection to latent structures tend to be robust when there is some noise in the x or the y values. That's because we're not looking at the original measured values. We're looking at the principal components derived from the original values. And noise automatically gets filtered out when we generate the principal components because we're reducing a large set of variables down to a smaller set of variables, and noise is not a particularly important feature of the big set of variables, so it gets eliminated That leads us to another really nice aspect of principal component regression or projection latent structures. It extracts information from the ensemble of data. So even though you've condensed your problem down to, or your understanding of the situation down to a much smaller set of principal components, those principal components can contain data from all of your original measured variables. Also, for projection to latent structures or principal component regressions, you don't need a large number of observations. You only need to have a number of observations greater than the number of principal components you're using in your model, not the number of original variables. So if you had that situation where your refinery had 500 measured variables, to do multiple linear regression, you need to have 500 observations. That is 500 points in time. You need to measure your full set of variables in order to generate your model. With principal component regression, projection latent structures, if you're only using 3 to 5 principal components, in theory, you can generate your model using 3 to 5 observations. So at 3 to 5 different points in time, you measure the values, your entire measured set of variables, generate the principal component observation values, and use that to come up with a regression. Now, many of these advantages are also applicable or true for artificial neural networks. However, compared with artificial neural networks, principal component regression and projection latent structures do have one advantage, and that is they have less potential for surprises. Artificial neural networks are black boxes. When they misbehave, it's virtually impossible to understand why they're misbehaving. And sometimes they can misbehave or give strange predictions in a very unexpected way. So for example, this is a constructed example, but it's a real example. The image we have here has been run through a classifier that attaches a probability to a number of different labels. So for instance, it looks to see whether this is broccoli, a burrito, a ladle, a soup bowl, a tabby cat. Obviously that would be a good choice. This is a tabby cat. Or whether it's a cucumber or a plate, etc. But this classifier, which generally works really well, has been tricked by this image. Rather than saying this is a tabby cat or some sort of cat, or maybe saying this is an animal, or saying this is a stuffed toy, it associates a very high probability with the label for guacamole. That's a really unexpected result. So projection to latent structures and principal component regression may not be as precise or as capable as artificial neural networks, but on the other hand, their output is a little bit more predictable and unlikely to give you strange results like this. Finally, we can use Explore for process monitoring and fault detection. Process monitoring applies techniques normally associated with monitoring of a single variable, for instance, a measurement of quality, to the ensemble of process variables. It allows for faults, that is, periods of low efficiency operation or deviations in the process or material or sensor failures, to be detected through multivariate control charts. So if we're just looking at a single variable, we use a univariate control chart, but here we're talking about multivariate control charts. And the diagnosis of the failures can be achieved through a better understanding of the process as revealed by our descriptive models or predictive models, and hopefully this will allow us to adjust the process when necessary, either to avoid faults or to return the system to its optimal operation when a fault occurs. Now, why should we be looking at multivariate statistical process control as opposed to univariate statistical process control? Well, let's look at an example. So here we have two measurements, or two variables being measured. One is y2, so that's on this axis, and we see the different values at different times on a scatter plot here. And the other one is y1, that's along this axis. We see the different values that have been measured. And we have univariate limits, control limits on these charts. So For this variable, we have this upper control limit and this lower control limit. And for this variable, we have this lower control limit and this upper control limit. And if we see the measurement going outside of these limits, then that should trigger some sort of investigation. That's outside of what we consider normal. Now we have a measurement at a particular point in time being indicated by a circle with an X in it. That's shown here, and the concurrent measurement for Y1 is shown here. And we can see these are well within the control limits. So looking at Y2 and Y1 independently, we see no problem. But if we now look at them on a two-dimensional graph of Y2 versus Y1, we see that this is in fact an obscene outlier. All of our other variables are correlated in a way such they fit within this oval here. And for this sample number, that correlation is completely broken, and it sits well outside this typical oval where the points, all the other observations lie. So that shows how a multivariate analysis can reveal information that a univariate analysis cannot show. Here's an actual example taken from the literature. It's a distillation column example. In this distillation column, there are a large number of measurements being taken, and based on those measured variables, the values of the first and second principal components are calculated. And these are shown on this graph. Each day we have a new measurement for the principal components, and for the first 400 days, these measurements fall within this oval here. And then from day 401 to 490, we see these values for the principal components shown with little cross hatches here. And we can see that this is a very different regime of operation than we had here. Now in the real world, it took them 90 days to really figure out that this was a problem. It was associated with some undesirable aspect of operation, and to fix it. But if they had been monitoring these principal components, they would have quickly observed that there was off-spec operation here and got an idea of what was causing it and fixed the problem. That's what I have for this webinar. If what you've seen leads you to believe that you're interested in either Explore software or Explore training, what can you do next? The good news is NRCan plans to offer online training in Explore coming up later this year, we hope. So if you're interested in that, write to info@rerinfo.ca, that's me, and I will put you on a mailing list to let you know when these courses are being held. You can also write directly to NRCan. If you look up Explore software, you can find links for them there. Thanks very much. I hope this has been useful to you. Don't hesitate to contact me with questions as well.